Okay, let's start solving some problems in order to clarify the concepts. First problem. We have that system. G is 200 over s plus 2, and H is 1 over s plus 4, s plus 5. And now we want to find out the gain margin and phase margin. That's the first question. Let's go. Here we have the body plot. The full line is the condition we have, and then the other lines are solving the questions. The first question, which is the gain margin? We take the gain margin, where we take the gain margin? Who can tell me that? Gain margin when...
The top? Is it the top?
What happened?
Is it the difference in the top? No?
What happened there?
Okay. The gain margin is the top difference, no? When it's falling? No? Or am I wrong?
The gain margin is when the phase curve cuts the minus 180, and then we measure
When the magnitude dB is equal to 0.
we measure the distance from 0. The gain margin, remember the example with the nyquist plot that will tell us, let's say that we have something like this, and we have minus 1 here. The gain margin is this section. And in body, it is, if we have body, let's say that we put body here, we have this is the magnitude, and here we have the phase, the angles, phase. And let's say that here we have minus 180, and we cut, when we cut here, for example, and then when we cut minus 180, if the gain is less than 1, in dB it is 0, then for this case, where we have, if we don't have poles on the right half of the planes for the original function, for the open loop transfer function, and we have no ends, as we can see here, then the system is stable, as is represented here, a stable system. N equals 0, because it does not encircle the point minus 1. And then, having that, we have, according to body, that this is the gain margin, which is this in nyquist. Now, the phase margin. When we cut this point, which is 0 in the body plot, but it is minus 1 in the nyquist plot, then when we cut that, we should have, if we make a circle here, then we see that in order to not cut the point minus 1, the gain of the system, when the system, the phase of the system has to be here, and it has to be here. less than minus 180, numerically, I mean, less than minus 180, so it didn't reach minus 180 in order to be stable, because if it cuts, if this were like this and cuts this, it will be 1 after passing minus 180, and then the system should be unstable. So we can apply the nyquist rules to the body diagram, and here we have the phase margin less than minus 180, and there you have it. Here the gain margin when the system cuts minus 180, and when the phase cuts 0, it is the phase margin. Know that both are positive. The gain is under 0 and the phase is positive. So the system is stable.
But how do you get 25 degrees from that?
What?
How do you get 25 degrees from that? It's not, I mean, it's not specific. There's,
25,
yes.
approximately. Any graph solution is not an exact solution. It
Right,
is
but I
valid
mean-
also for this.
There's like 90 degrees in between.
Well, we
one
have
and the
90
next one.
here.
How do I know it's 25?
We have 90 here,
Right.
and we have minus 180, so it is between minus 90, it is more than 90, near to this. This angle is approximately, let's say that it is 165 or something like that, and it is approximated, depending when you do a graph, depending on the quality of your graph, you have a better or worse solution. And then-
Also, that line is, let's say, at 155.
Well, it's
then
not
from
25,
from
it is
155
32 or 22.5, okay? Whatever you want.
Yeah,
but
but
it is positive.
What I'm saying, Professor, is so that she understands, because I think she's a little bit
Mhm.
still thinking about it. So
It is
that
a
line is
positive
more or
number.
less at more or less at 155,
we
and the
are
difference
not-
between 180 and 155 is 25. That's how he gets the 25.
We are not that interested in the number. We are interested in looking that this is positive because it didn't reach minus 180. It could be, let's say, 165, 152, 182, or no 82, 172, whatever, but it is positive. And what I gave here is the approximate value as the one that I gave here, which is an approximate value. Why? Because we are dealing with a graph, and the graph never gives the exact number. Now, we can calculate that if the gain margin, as we have seen, is 6 dB or 25 degrees positive, so the system in our conclusion is stable. Now, how much do we have to increase K in order to make the system unstable? So, what means the gain margin? Is the quantity that we need to increase the gain in order to move the system to the unstable position. So, we have to increase 6 dB in order to get this 6 dB. If the response passes through 0 here, then the system is in the margin of stability. And so we have to increase 6 dB in order to take in order to get that 6 dB up, in order to get the system in the limit of stability. And then, according to our graph, which is a logarithmic graph, we know that 20 logarithm of Ka has to be 6 dB, or Ka has to be 2, according to the elementary mathematics that we know. And then the K has to be not plus 2, but times 2, because we are dealing with the logarithmic scale. And then for a K equals to 400, the system will move to this dotted line that we have indicated there, which is the limit of stability. Of course, in order to find the phase, we know that the system now cuts 0 at some point, which is around more than 180, minus 180 degrees. So the phase also has been changed, because here the phase in the system doesn't change, but the gain, if we are looking for another position, then what changes is the gain, the response in the magnitude, because we didn't affect the poles or zeros position, we only affect the gain, which is 200 here in this case, and will be more 400 in this other case. So when we have 400, the system is for K equals 400, the system will be in the limit of stability here. And now, if the other question, what value of K gives minus 20 dB? So if I am at minus 26 here, I am here at minus 26. Or minus 6. I am here at minus 6. If I want to be at 20 plus, I have to move 26 up, okay? So I move 26 up, and then I have the K that I have to increase in order to have the system working at 20 gain margin, or minus 20 gain margin, because it is evaluated 20, but the gain margin will be minus 20. So I have to increase this number. So that's the quantity I have to move, and for this new curve, 20 dB up, 0, then it cuts the 0 dB at this value, again approximately value, because I don't have the way of knowing exactly on that curve which is. But I see that it is negative, so it passes minus 180, so it is unstable. Some questions? Now let's take another system. In this case, we have zeros on the right half of the plane. Why I know that? Because I have a negative number here. So when I solve this, it will give me some positive real part. So that means that I am with the zeros on the right half of the plane. Of course, this doesn't affect nyquist because nyquist looks only to the poles, to this. And all the poles here are or on the imaginary axis or on the negative part of the plane. So I have that P is how many? What is the value of P?
3.
What?
Is it 3?
0. I don't have poles on the right half of the plane. P, by definition, in our nyquist program, is number of poles on the right half of the plane. Then, if there are no poles on the right half of the plane, P is 0. In order to be an stable system, it has to comply with this. If this is 0, in order not to have poles for the closed loop system on the right half of the plane, N has to be 0. Do you agree? Well, there you have the nyquist program for obtaining this, and there you have the plot, the nyquist plot. That is done with MATLAB, and there you can see that it cuts. Know that MATLAB gives you these values. I put it there, but, well, not all of them, but the basic one, the point of intersection. It is 0.717, meaning that the point -1 is outside this graph. So it is not encircled. So it is 0 encirclements, and this is 0. So that system, in the way it is presented, is stable. What is the gain margin? Well, you know, by definition, and we proved that previous classes, that 1/A, which is this point, if you calculate this, then A will be the inverse of this number, and the gain margin will be given by this number, which is 2.86, which is positive because the system is stable. So question here. Now, look to the body. There we have problems. MATLAB gives, of course, the correct answer, but if we try to see that in the, as we learn about body, the first thing we note is that it is not saying about -180, it is talking about 180, positive. So the graph here does not comply with our requirements. So you can get that still, you can get that in this case if you take into consideration that you are taking near, so this point, which is the point where the function cuts the 0 dB, the angle is more than no, you're taking this like this way. This will be -100, this will be plus 180. And this is, let's say, 200, 202, 203, 207. So in this case, the phasor is in the proper place, but indicated not the way we have learned. And then this is an example why we do the body, if we take into consideration that we are talking not about minus 180, but plus 180, taking that into consideration, then we can say the system is stable from the response, from body response. And when we take the cutting, there we have 0 and we have 180. In this case, 180 is the same. If we take it this way, it is the same as minus 180 if we take opposite. So you see that the problem complicates. And then, again, don't use body if you have poles or zeros on the right half of the plane for the open loop transfer function. This is another case. Is that system stable or unstable? We have a nyquist plot there. It is marginally stable. Let me see.
It's at minus 1. It's at minus 1.
Yes, minus 1 is here. So it is marginally stable because it is cutting. It doesn't have poles on the right half of the plane. So P is 0. You agree? P is 0. And then N has to be 0. If we take a gain smaller than 1 there, the curve will contract. And then the system will be stable. But if K is bigger than 1, in the case of K equals to 1, we have this situation here. But if it is bigger than 1, the figure expands, and then the system will enclose at least one pole, and at least the point minus 1 at least one time, and then the system will be unstable. But in this case, it is marginally stable, which for us, the practical point of view, it is unstable. No questions? Well. This is the body plot of this. Not the best. It's not the best. There it says that the system is unstable. In reality, it is marginally stable, but we can say that the system starts being unstable at this point. Note that the gain is 0, the gain of the system, the angle does this, and then you see it is not 180 but minus 180, or in place of having minus 180, it has 180. So again, the response from body is not good. May be correct, a lab can do it, has the correct response, but it's not good for us to work with it. Now we have here K. If K is big for this function, then it will expand and encircle the point minus 1 and will be unstable. If K is small, smaller K gives more stable systems, because the system will cut the point, the real axis at minus 1, exactly at minus 1. here we have a system. Know that, look to the body plot. The gain margin is infinity. Why it is infinity? Because the function never reaches minus 180. It reaches minus 180 at infinity, and at infinity the function has an infinity value, or minus infinity. So the gain margin is infinity. And the phase margin is given here when you cut the 0 dB, then you have the phase margin there, which is all the time positive because the system never reaches the 100 minus 180 angle. And then this system is always stable for any value of k. The problem is when the gain is too big, then this figure is moving to the left, and then you may have the gain margin reduced, but in this case it is stable. I have talked about this in the past. If you don't have poles on the right half of the plane or zeros on the right half of the plane, then the system is, we say that it is a non-minimum phase transfer function, which is acceptable for using body. If the system is non-minimum phase transfer function, the stability should be determined, not using body, but using root locus or using nyquist, any of them. And then you do whatever you want to do with the system using body. But if you want to include regulators or something like that, but all the time calculate the stability based on nyquist on root locus. Now let's see this system. How many poles do we have on the right half of the plane? No poles. All the poles are
On the left.
all the poles are on the left part of the plane, as you can see here. Minus B, which is a minus. And then the system has no poles on the right half of the plane. If we do one nyquist plot, if the nyquist plot doesn't cut or doesn't encircle the point minus 1, then the system will be stable. Let's see. We have this here. Know that, like a second order system, there is one curve going up. Then the gain margin here is infinity because the system never reaches minus 180. But the phase margin is not infinity because of this small curve here, and then you take it cutting here. Of course, it is positive before 180, but with a number which is not infinite, which is okay, no problem. The system is stable all the time. Let's see what happened with this one. We have the program for nyquist. That system. What can you say about the stability, the system stability? P equals 0, no poles on the right half of the plane for the original function.
Stable.
Not encirclements of the point minus 1. So Z is 0. Okay? So the system is stable, as can be seen there. It doesn't circle the point minus 1 anytime. The gain margin, when it cuts the real axis at 0. So gain margin given by 1 over A will be infinity. So the gain margin is infinity for this system. No questions?
Okay, you repeat one more time with A is equal to 0?
What?
Can you repeat one more time with A is equal to 0? The y 1 divided by A.
I don't understand you. What?
Like y, the gm, that is 1 divided by A. The A is
Oh, that is by definition. Have you opened your classes, previous classes lately?
Yeah.
But we said from the beginning, when we started studying nyquist, that the gain margin is given by this relationship. The gain margin is given by this quantity. This is 1 over A, and when we did a simple calculation, we found that the gain margin is 20 logarithm of A, where A is given by this point. If this point is 0.1, A is 10. If this point is 0.01, A is 100.
Okay.
And then that's what we accepted. And then accepting that, we have that the gain margin is 20 logarithm of A. If A is 0, then the gain margin is infinity. Gain margin infinity, as can be seen here. The phase never reaches minus 180. So the gain margin is infinity, at infinity. The gain margin is infinity. And the phase margin is the point where it cuts the 0 dB somewhere by here, around, again, around, not exactly, 130 degrees. And the rule locus is shown there. We have poles on the axis and on the left part of the plane. Let's see the stability of this. Again, we use MATLAB. Know that here we have poles on the right half of the plane. You see that? Poles on the right half of the plane. 3, well, we have 1 on the imaginary axis, if we go to rule locus, and 2 on the right half of the plane, and zeros, we have also 2 on the right half of the plane. But when we apply nyquist rule, number of poles on the right half of the plane for the closed loop system is P. P is 2 here. Well, could be 3 if we take into consideration this one, but it is not considered. It is at 0, not positive. And then we have 2 poles. Z is equal to 2 minus n. So if n is equal to 0, the system is unstable. Let's see what shows the diagram. The system is, as shown here, stable, because the point minus 1 is far away to the left. It doesn't encircle the point minus 1. And the body shows whatever here. You can check, looking carefully. It cuts 0 dB at an angle of minus 80. It cuts the 180 or minus 180. It doesn't cut it. Minus 180 never cuts it. So it could be anything in reality. It could be stable or unstable according to our analysis in body. But what gives us the truth is the nyquist. So when we have those situations, we need to go to nyquist always. The real locus, now that we have two poles on the ray half, one on the imaginary axis, and two zeros on the ray half of the plane. As can be checked, look into the function. Two zeros on the ray half of the plane, and two poles on the right half of the plane, plus one over the imaginary axis. Locus also shows us very clear that this system is unstable, but bode doesn't show that. Bode should not be used in such situations. What are the advantages? Then you can say, okay, then why to use bode plots? Bode plots has several advantages, even there. It is easy to work with it. You can see better with bode, the gain margin, the phase margin, better than with nyquist. And of course, on true locus cannot be seen that. It is easy to see that. If you need to work with controllers, it is easier to add controllers and see how is the effect of these controllers on the system. So those advantages make the bode plot very useful in many applications with the limitations that I have given to you. Now I want you to see the relationship between all that about poles and zeros that we have studied here and what we are used to see, like the response, the system response. Note here that when the system, I am taking an ideal system as the reference. For some value here, the system is stable, and we have an underdamped system which is stable. Here is the resonant point, which has a value at some frequency. If we move our system to the left, then the system becomes more unstable, as you can see there. And the point where here was not that well seen, the resonant frequency was not very neat, but the resonant frequency here is better as the system moves to the left, less stable and having a better resonant frequency. When it crosses the point -1, it is an ideal oscillator, and the resonant frequency goes to infinity, as you know, theoretically with the oscillator. If it surpasses that point, then there is no meaning in talking about resonant frequency. That has no meaning, this response. And the step response goes to values that make the system unstable. Let's see the system. The point -1 is here. Then the system is there in the limit of stability, according to nyquist. If we see we have 0 poles for the open loop system on the right half of the plane, we have no encirclements because this point is out of the encirclements. So n is equal to 0, p equal to 0, so the system is stable. But what happens if we increase K, I believe, okay, I have it, in that case, I have it here, I jumped it. For a bigger value of K, then the point minus 1 is encircled by, the point minus 1 will be somewhere by here. It is encircled twice by the system response. And then n is equal to minus 2 because it is done in the clockwise rotation. P is 0 and the system is unstable. If we reduce the gain, is the other case where it was being calculated. This, by any means, could be, for example, even in Rouhorwith, the value that makes the system marginally stable. And then it was calculated at 5.6. And then when I give to the system 5.6 gain, then we have this. The system is at a point very near to start being unstable, but it is not unstable yet, because still the encirclement is 0. And you can see the body, well, the body for this case, it is clear. You can check that when it cuts, the 0, the phase is under 180 minus 180, and it never reaches the phase minus 180. So the system is stable in this case, still. But if we amplify the system response and the K 100, then the system encircles both, and then you will have here with body that it cuts, the face has no problem, but the margin here is, now that it is not seen very clear, but it is positive. So the gain margin is negative and the system is unstable. Four poles on the right half of the plane and 1, 0 on the right half of the plane. Let's see this other situation. We have the nyquist plot for this. We have one pole on the right half of the, or 1, 0 on the right half of the plane, and the 4 poles on the right half, or the left half part of the plane. So, n p equals 0, because the poles are all on the left part of the plane. N is equal to minus 1. Note that it is encircled minus 1 time, and Z is equal to 1. So this system is unstable. You see that? We have that. Here again, the system may show some stability when it is not real stable. We have here the angle to minus 180, and we have that we cut, this is 180 here, yes, minus 180 here, and we have the zero cut here, but it is positive, it is not, the phase here is positive and less than 180, so it is unstable there. But the body plot doesn't show it very clear. If we increase, that's what I was telling to you the other few minutes ago, if we increase the K to 10, then the volume expands, and then the system cuts the -1 and this one time, and the system is unstable. Okay? Questions? No questions? I will bring some charts, some curves next time in order that you practice doing this a little. And after that, we will have the review of the test. Okay? Okay, it's finished. That is it.
Shall we do you have it?